G'day everyone and welcome to Tunnel Fires, when design, science and emergency response collide. This webinar is being hosted by the Institute of Fire Engineers Australia branch, and we have to shout out to the board, especially Marianne Foley, for putting this webinar together. My name's Gerard Mann and I'll be your moderator tonight. I'll be introducing the speakers and I'll be asking questions that you put in the chat. So without further ado, we'll get into it. Start with the welcome to country, and I'd like to begin this by acknowledging the traditional owners of the lands on which we meet today. I would also like to pay my respects to elders past, present and emerging. Tonight's webinar offers 1 hour of CPD. So for IFE members, we are offering that 1 hour. Please email membership@ife.org.au with the subject of the email as IFE Australia Tunnels Fires webinar to organise your CPD certificates. And that's for everybody who's attending. I know we've got a lot of people from overseas and international tonight online. If you are chasing your CPD certificate, please email membership@ife.org.au. All right, a quick disclaimer now. So any views or opinions expressed or implied on any matters by the authors, presenters or participants during or in connection with the content of this presentation are solely the views of the authors of the respective comments and or opinions, and they must not be taken to be views, positions or policies of IFE. IFE makes no representations, warranties or assurances and accepts no responsibility for the content and or accuracy of this resource. IFE shall not be liable for any damages, including, without limitation, direct, indirect, incidental, special, punitive or consequential damages that result in any way from your use or reliance of any content from this resource. All right, so now with that out of the road, we are looking for more memberships. If you are interested in IFE membership levels, we have the student, technician, graduate, associate, and member and fellow levels. Please contact us at membership@ife.org.au, or for more information, visit IFEA or the Institute of Fire Engineers Australia. And I've got the URL down the bottom there. If you enjoy tonight's webinar, please consider giving us some membership. The more membership we have, the more webinars we can put on, the more conferences we can bring you. Speaking of conferences, AFAC's coming up in August. We have an IFE AFAC stream. We're lucky enough to have 2 speakers tonight present at our AFAC stream. So please come along if you are coming to AFAC. So tonight, the subject, tunnel fires, when design, science and emergency response collide. Tonight, we want to discuss our understanding around how tunnel fires develop and behave under real conditions. We want to explore ventilation strategies and fire dynamics in the confined transport systems. We want to gain insight into firefighter decision-making and the operational challenges of fighting fires in tunnels. And we want to learn how tunnel design, standards, and risk management influence the safety outcomes from building tunnels. So without further ado, I'd like to introduce Dr. Ricky Carville, Professor, Edinburgh University, who's going to talk to us now about fire dynamics in tunnel firefighting. So I'll let Ricky share his PowerPoint.
Okay.
Anytime.
Hopefully you can hear me, and I'll try and share my screen. I'll just carry on assuming that you can see my screen and you can hear me. If that's not the case,
We can see and hear you, Ricky.
somebody shout out. So thank you for the invitation to present today. I've only got a few minutes, so it was actually a question of what on earth do I speak about when in such a short period of time that's actually worth talking about. And so I landed on this title. It's a slightly clumsy title, but it's "We have a tunnel ventilation system. How fast should it blow?" And this is a question that I've seen addressed at conferences, in journal papers, in design meetings all over the past 20 years, really. And my slide is not advancing. Why not? But before I get to the question of tunnels, I want to address what is fire safety engineering in its most wide form. And that you may think is a strange question to put in front of the IFE, because surely we know what fire safety engineering is. And I actually, for a long time, thought I knew what fire safety engineering was. And then through years of teaching students, and I did look through the list of participants in the room there, and I see some of my former students in the room. So, hi guys, good to see you again. Um, Particularly shout out to the IMFSE students in the room, or the former IMFSE students. Um, but actually, I worked as a fire safety or educator of fire safety engineers for a long time before I realized that fundamentally the main aim of fire safety engineering is really quite simple. And our job is to keep people and smoke separate for as long as we possibly can. And hopefully we do that in buildings. We aim to not have people and smoke interacting at all. Um, and so you get everyone out of the building is as designed, hopefully, before the smoke gets there. Um, so that's why I say hopefully indefinitely. But smoke management in a tunnel is a more complicated thing than that because we can't simply open a window, open a vent, and let the smoke go outside and it magically goes away and it becomes, the atmospheric scientist's problem, not my problem. Um, so typically in tunnels, we use mechanical ventilation, jet fans, or sometimes different ventilation systems. But increasingly over the past several decades, if you've ever passed through a tunnel, what you'll have seen is something not completely unlike the picture shown on the screen there, with some jet fans mounted on the ceiling, sometimes mounted at the sort of corners of a rectangular tunnel or whatever. Um, and those jet fans, well, they're not completely a smoke control system. They're actually there for environmental management, for pollution control. And what they do is they move air. But if we get it right, we can move air to move smoke where we want the smoke to be, um, and gain some form of control over the smoke. The theory goes something like this, and I'm sure many of you will have heard talks on smoke management in tunnels before. Um, but if you have a horizontal tunnel, which of course is a very rare thing because tunnels generally are going down under things, up slopes, um, and so actually, we never have this idealized situation, but we always start with an idealized situation. You've got a burning object in a tunnel, it produces smoke, the smoke rises, it hits the ceiling, and it spreads in both directions. Of course, remember that this a tunnel's a long, thin thing, so while there is some movement of smoke into and out of the frame, it doesn't go very far before it starts going longitudinally. If there's no wind, if there's no mechanical ventilation, it spreads both ways and it kind of stratifies where the smoke stays up because it's hot, which means that the people running away underneath the smoke, and I've drawn them as running away there, uh, we usually assume that they're walking, but in reality, if you see smoke moving above your head, which is faster than you can walk, your gut instinct will be to move a bit faster. And you will start to find people running away if the smoke is spreading above them. Of course, the problem with the hot smoke if it's hot, it stays up, but as it travels, it cools down, and some distance from the fire, it may actually descend and get in people's way. And that is not an ideal situation. So we need to manage that smoke somehow. So, generally speaking, in modern tunnels, we manage that smoke by blowing longitudinally along the length of the tunnel. Uh, and as soon as we start blowing from one direction, um, the bulk of the smoke's going to go the other way. It's going to go downstream, the smoke's going to blow it away. Now, that doesn't mean that all the smoke goes that way. Sometimes we get this situation where even though we're blowing left to right, as shown on my screen, you do get some what we call backlayering or backflow, where the smoke advances along the ceiling against the overwhelming ventilation flow, simply because there is power behind the fire. The fire is a source of energy. It's pushing the smoke, and that smoke is going to push against the ventilation, and we might get what we call backlayering or backflow. But if I increase the ventilation sufficiently, you can see that my little drawing of the girl running away there. She's now happy because there is no smoke above her head. Um, we push the smoke back. All the smoke is directed downstream of the fire object. Now, whatever the fire object is, everything downstream of that, we've now lost all stratification. There's no fresh air to breathe on the right-hand side of the fire, which is a problem, certainly for anyone on the right-hand side of the fire. Um, but this condition has been the holy grail of tunnel safety design, achieving what we call the critical ventilation velocity, that enough air is blowing such that all the smoke is blown one way and the tunnel is clear in the other direction. And I have to say, and I have been going to conferences run by the tunnel safety community for over 25 years now. The tunnel fire safety community is completely obsessed with the concept of critical ventilation velocity. In fact, if you look at journal papers published just last year, in 2025 alone, I counted 16 journal papers in peer-reviewed journals, not counting conference papers, not counting other things, that all offer something on the subject of critical ventilation velocity. That's 2025. I could do the same in 2024 and 2023, all the way back. For the past 20 years, there's been 10, 15 papers per year redefining, coming up with a new equation, telling me something about critical ventilation velocity. I've reached breaking point. I don't read these papers anymore. Because actually, critical ventilation velocity is fairly simple. If you go back 30 years, um, Oka and Atkinson came up with this graph on screen here. Basically shows that up to a certain fire size, there's a variation of ventilation velocity with heat release rate. Once we get to that bend point in the curve, we don't need to put more ventilation in to control smoke from bigger fires. And very approximately, it's about 1.1 times the square root of the height of the tunnel, ish, plus or minus error bars. But we generally will design a tunnel for with a safety measure anyway, a safety factor in there. So we don't need absolute precision in calculating the critical ventilation velocity. And yet all these papers come out every year, which, as I say, I've had enough of. I'm actually, as I've been mentioned, I'm coming to Australia in August for the AFAC, for the IV conference stream there. And if you go to that website at the moment, it will tell you the title of my talk is Road and Rail Tunnels, Challenges and Solutions. But actually, I was considering doing a talk about why I don't care what the critical ventilation velocity is. Um, because the tunnel industry is obsessed with it, and it matters, but it doesn't matter that much. There's other things that we need to care about. So I've talked about smoke. What about the fire? Because when we blow on a fire, we change the fire. So here's some heat release rate data from a few experimental campaigns that have been carried out in tunnel fires. Hopefully you can see four graphs on screen, one red one orange one. They're a subway carriage from the Metro project and a railway carriage from Carleton University's fire test, both done about 13, 14 years ago. The other two are both railway carriages from the Eureka project, both done about 30 years ago. Now, the shapes of those graphs are rather different. And this is a question that we need to think about when we look at, and I realize some of you care about road tunnels more than rail tunnels, but the same pattern approximately, if I'd put bus fires in here, you would have got the same pictures. So some of them have a short period of growth, a couple of minutes. They then appear to have a very rapid fire growth to a high heat release rate. I mean, if you look at, I don't know how easily you can see the numbers on my screen, but those graphs on the left-hand side are going up to 50, 60, 70 megawatts of energy release within 10 minutes of ignition. That's actually insane. If you're used to dealing with fires in the built environment and buildings, you might be talking about things going to 3 megawatts in 10 minutes. No, we're going to 70 megawatts in 10 minutes. Um, it's, I mean, literally an order of magnitude bigger. Um, but some of the data, the ones with the blue and green graphs on the right there, you'll see they're growing to, I mean, 10 megawatts. It's still not a small fire. It's still a very large fire, but it's taking 20, 25 minutes to reach a peak, and then it's burning for an extended period of time. So the question is, why do some carriages burn like the ones on the left, and why do some carriages burn like the ones on the right? And the answer is simple. The ones on the left were in experiments where we had the ventilation switched on. And the ones on the right were in experiments where the ventilation system was not switched on. In fact, they were measured in place to reduce the longitudinal flow. In other words, what we do with a ventilation system during a tunnel fire affects the dynamics of the fire. This should not be a surprise to anyone. Blowing on a fire changes the fire. We should know that, but sometimes we kind of forget. And we use blowing at the fire as a strategy, which maybe is not a great strategy. Now, what I've got on screen here now is a table. It's a very simplistic table, and given the time that I've got to talk, it's about as complicated as I can get. I will go into this in more detail in the talk that I come back to do in August in Melbourne. So if you want to hear more, come back then and you'll hear about that. But if we just look at ventilation as a smoke control mechanism, um, then when we can go from low ventilation to high ventilation, we certainly eliminate smoke from the upstream side of the fire. But if we look at what's happening on the downstream side of the fire, where is their control? It's a smoke control system, but we've controlled it in an uncontrolled manner, which is kind of counterintuitive. We've got a huge problem if there's anyone on the downstream side of the fire. And if there's anything I've learned from looking at data from tunnel fire incidents over the years is that the people in the tunnels do not behave in the way you want them to. I think that basically happens in all fires. But people do weird things, and they will end up where you don't want them to be, where you didn't intend them to be, where your design doesn't want them to be. And you need to think about what to do with that. But it's not just a smoke management system, because when we blow in the fire goes from being a small, slow-growing, slow-spreading thing to a large, fast-growing, fast-spreading thing. And what we do, and what we do with the ventilation as a design choice, influences the fire. It actually also influences the smoke properties. So when we're underventilating the fires, they're very nasty. The smoke is very nasty. It's got lots of toxic stuff in it. The more we blow, the more we dilute the nasty stuff, but we don't get rid of the nasty stuff. It's still there. And I put this up on screen basically to say, think about the whole problem. You're designing a ventilation system for smoke management, but what other effects will it have? Think about the whole picture, and you'll get somewhere. And that's basically where I want to end up. Is our job as fire safety engineers is to keep people and smoke separate for as long as we can, hopefully indefinitely. But how will that work in your tunnel, in the subway system that you're concerned with, when you've got merging flows and all sorts of complicated things going on? How does that actually work in reality? And that's a conversation we can't have in 15 minutes, but we can maybe have in longer form in the future. So that's all I want to say to you this morning from my point of view, this evening, if you're in Australia at the moment. Thank you for your attention. Hopefully, I'll get to see you in Melbourne in August. And as I always do, there's a plug. There is a book with my name on the cover, um, Handbook of Tunnel Fire Safety. The third edition, we're still talking about, but it's not written yet. So at the moment, the second edition is where we're at. But anyway, thank you. There will be a Q&A session in a little while, I think after all three speakers have spoken. So please do send your questions and we'll get to those. Thanks.
Thank you, Ricky. Great presentation for a 15-minute presentation. I know it's very short and not a lot of time to be able to convey your message, but I can see exactly why you're internationally recognized for your contributions to fire science, especially ventilation and fire safety engineering. That was brilliant for someone like me who's an operational station officer. I understood every word of it. It wasn't too complex. You made the graph simple. So thank you very much. I'm really looking forward to seeing your lecture later in the year at IFE and AFAC. And I'm really looking forward to the question and answer period, which will be at the end of the session. Now I'd just like to introduce our next speaker, and that is one of my good friends, Carol Lambert. So Major Carol Lambert is a Belgian fire officer with the Brussels Fire Department. He's internationally recognised as a lead instructor in the CFBT world, and he is the head instructor of CFBT Belgium. He has a background in engineering, occupational safety, and fire safety, and he has contributed extensively to firefighter research, training, and doctrine. He's a long-standing member of the International Fire Instructors Workshop and is regarded globally as a leading voice in modern structural firefighting and operational decision-making. So thank you, Carol. I'll now hand the screen over to you.
Okay, I'm going to start my PowerPoint presentation. Do you guys see that?
Mate, that's up. Thank you.
Okay, great. So I'm going to follow Ricky's example. Shout out to IMFSC. I'm an IMFSC graduate myself, and I've been teaching at Ghent University since I think 10 years. Now I'm more here like in an operational role, so I'm going to talk a bit about tunnel firefighting. I'm going to get this up and running. This doesn't work. Why? My slides are okay. 10 years ago, I went to this fire. So this is the entry of the Brussels Central Station. So it's a huge building. Most of it is underground, and there is the most important rail connection in Belgium is going underneath this building. And this is what we saw when we arrived. There was a fire, and this is 2 floors above the level of the tracks. And so we didn't know very well what's going on inside. There's not so much smoke, but enough so you have to put on your SCBA mask and you start consuming air. So it was 9 years ago, actually, just before 5 o'clock in the morning. The picture you see on the right is the visibility on the tracks. So still, it's not zero visibility, but there is some restriction visibility, and you do need to consume air because there's too much smoke. Visibility was about 10 meters. There was a construction train on fire, and we started an attack from the point where the first picture was taken up to the fire, which was 340 meters long. It took us 22 minutes to establish an attack line. During that time, you're working hard, you're using air. So 3 minutes after that, the first guys went on whistle and guys had to turn back. These are some pictures of the fire. So the fire wasn't that big, a couple of megawatts. And also because of the time it took us to get there, maybe the fire was already in decay when we started our extinguishment. After knocking down the fire, we started boundary cooling. So you don't only need water to extinguish the fire, you also need water to cool the concrete structure, because if the heat release goes up, temperatures goes up, you get spalling, you might have a problem with structural stability. So the rule we have is 1/3 of the water is used to extinguish, whilst 2/3 are used to cool the structure of the tunnel. So if we look at the factors in our favor at that fire, it was a relatively small fire. So maybe 5 to 10 megawatts. It was very early, so we had very few commuters in the station. We started 3 years prior to that a tunnel firefighting training program. The past 10 years, we sent 300 to 400 people to Switzerland for a week tunnel firefighting training. We had a couple of these guys in those crews, so that helped a lot. And it only took us 48 minutes to extinguish that fire. What were the problems that we dealt with? There is just too little air in SCBA sets to deal with such incidents. So the first crews who arrive on scene, they have a single bottle SCBA. It took time to get replacement crews on site. So the first crew knocked the fire down, but then had to pull out because of a lack of air. And at that moment in time, the replacement crews weren't there yet. So if the fire would have been bigger, it would have restarted, regrown, and would have to start all over again. Also, being on whistle, which means you have 50 bars left, 340 meters into a smoke-filled structure, not really the place you want to be with your firefighters. So that was an incident we had. We learned from it. The tactics that we use right now is very broad, same problem as Ricky. 15 minutes is actually very short to explain something. So we send in 3 types of crews. The first crew we send in is a very small crew, is going to do recce. What's going on here? What's burning? How many civilians are there? What are extra risks? Are there dangerous goods? That kind of stuff. So their job is to collect information and to send it to the command posts. The second group is blue. Their job is to attack the fire. And the third group is yellow, and they're going to rescue civilians. And they each have these lights with them to sign certain stuff so we can all be on the same page. The general approach is that we try to encircle the fire and we attack from downstream and upstream. So whatever happens, the fire should spread and we should be able to tackle it. The last topic I want to touch briefly is air consumption, because in the example I gave, air consumption was a thing. We didn't run into troubles, but it was stressful for some of the guys because they realized I used 250 bars to get in, and now I only have 50 bars to get out. Of course, you know the way, you don't have the heavy work of putting the lines in place, but still, that's a risk that's too much. So I started doing some research into air consumption, asking the question, how far can we go with a single bottle SCBA? And this is a scientific paper I published about the research project that I did a couple of years ago. So I took 7 engines offline, 7 appliances, as you call them. In our system, there is 6 guys on the appliance, 1 driver and company officer, station officer, as you call them, and then 4 guys. And we sent the 5 crews of 7 guys, the driver remains outside, into a 420-meter long tunnel, blindfolded, so to simulate zero visibility. We gave them a blindman stick because that's what we use for tunnel firefighting. And their goal was to find the victim at the end, put it on a stretcher, and bring it outside. So to give you some brief results, 44% of the guys went below 50 bars, which means that that's a problem. 16% of the guys ran out of air, would have died in a real incident. A large spread on the data, so execution times varied between 25 and 43 minutes. But an important observation was every queue notices the 175 bar signal, which signals that they used half of their usable air. So that's an important thing to have a safe operation. In reality, they will turn back at that moment in time. But in this experiment, they were ordered to push through. So some conclusions is they get used to the guide stick whilst using it, and that's why they become faster. So faster crews, they use less air overall, not per minute, but per meter that they do. All crews were faster on the way out than on the way in. So the velocities are the average velocity of the crew. That means practically is that crews can start with a single bottle. Yeah, as long as they return on the 175 bar mark, it's safe to start. Yeah, because you use less air on the way back than on the way in. And then a calculated maximum distance for a recce operation is 275 meters with a single bottle SCBA. So I put 35 people through the test, and that was the worst performing participant. So there is some conservativity, there's some safety in that number. And there is huge individual differences between the fastest and the slowest person. It's a big difference. So for the moment, I'm doing some further research. So I'm putting people on a treadmill with single and double bottles to see how much do they consume at 2, 3, 4, 5, 6 kilometers an hour. So we have them walk 5 minutes for each of those velocities with a single bottle, 10 minutes for each of those velocities with a double bottle, and every 5 minutes we measure air consumption and heart rate. And so the idea is that we gain insight in how much air we use and how far we can go to design our operations into tunnels, so to guarantee we can operate safely. So it was short. I'm open. I suppose it will be after the last lecture for questions, but this is a short presentation about this topic.
Thank you so much, Carol. I really appreciate you spending a very quick 15 minutes to go over what could easily be a 4-hour lecture just on your research alone. We'll have questions at the end. There's already a few coming in the chat, so please stick around for that. I'll just share my screen and we'll introduce our last speaker. So our last speaker tonight is Jason De Silva, who's the Principal Engineer for Fire Life Safety of Transport New South Wales. Not only is Jason the Principal Engineer Life Safety Transport New South Wales, he's also the National President of the Institute of Fire Engineers Australia. He's known for supporting professional development and advancing us across the sector in engineering, industry, and emergency response. He has extensive expertise in fire engineering, life safety systems, risk management, and strategic safety outcomes. And he's a strong advocate for improving fire safety standards, resilience, and evidence-based practice across the industry. So without further ado, I'll introduce Jason De Silva.
Thanks, Gerard. I'll just quickly share my screen. Let me know when that pops up, please.
That's up, my man.
Thank you. So I'll start out with a classic Australian g'day all, just because I know there's a lot of people from around the world, and it's really awesome to have you here with us. And what better way than to greet you in a classic Australian greeting. Just for a little bit of context, for those of us in Australia, I am in New South Wales. I live in Castle Hill, and it's actually the home of the Bidjigal people on Darug country. So like Gerard mentioned, I'm here in 2 hats today. One as the Principal Engineer for Transport for New South Wales when it comes to fire life safety systems, and I'm also the National President of IFE Australia, and it's really, really nice to have everyone here. Just a huge shout out. I've seen a few of the people in the room, and a lot of them are my rail fire guys that I work very closely with. So really good to see all of you there, and a couple of members from Sydney Trains too. And these are their trucks that they get to play with all the time, and the amazing job that they do. Just moving on to the next slide. Again, an acknowledgement of country from all of us. It is a very close connection that we all share with the land in Australia. Just to give you a context of what this presentation is about, I will be speaking more from an owner-operator point of view, building on what Ricky and Carol talked about. It gives you context of, in my presentation, I will be talking about how transport is set up. So there's a few people on the call that actually do work on a lot of our transport projects. So it kind of reaffirms that how a large organization like Transport for New South Wales is governed. I'll then dive deeply into the tunnel standard, which is TS 0008.3. That document is available on the website. Anyone can type those numbers in and access that document for free. And then, like Gerard mentioned, there'll be question time later. So just to give you context of who we are as Transport. Transport's a massive organization with nearly 33,000 employees. So we are led by the Secretary of Transport. And under the secretary, there are certain divisions that work under him, being legal and governance and strategy. Then under that, we've got different divisions, which is safety, policy, environment, and regulation, planning, integration, and passenger. That's where I work. Operational groups, that the coordinator general, road maintenance teams, and resilience, Sydney Trains, New South Wales Trainlink, and Sydney Metro. For us, Sydney-siders or New South Welshmen will all know these entities as we interact with them every day. A big part of transport, obviously, is our project delivery teams. This is where a lot of our co-engineering strength sits. These are the project engineers that are dealing with delivering projects every day. So there's a big tunnels team there, and there's a lot of knowledge to gain from that team. They come under the infrastructure projects and engineering group. Then, of course, we've got our HR and our finance teams that take care of everyone else. And the massive beast that transport is, we also have got Port Authority. We work with the Office of Transport Safety when things go wrong and how we can make things better. We've got the Transport Asset Manager Group that owns the transport assets, and then New South Wales Motorways. To give you context of how big transport is in the tunnel space, as of 2025, we have 68 rail tunnels, 31 kilometers of metro twin tunnels, 24 road tunnels, and it's growing. This is just what we've reported so far. Everyone's aware of all the big construction projects taking place around Sydney to expand the network so we get better public transport access for everyone. Again, like I mentioned, the team that I work in, or the division that I'm part of, is the Planning, Integration and Passenger Division. We're driven by strategic assessment and prioritization of customer and asset priorities. And also we serve as the technical authority for transport for New South Wales. So what that means is we're the ones that set the standards and the requirements. These standards then go on to serve as base minimum requirements on projects. And the way we write these standards is it's written throughout the entire life cycle of an asset. So from the time we conceive it, plan it, create it, which is where a lot of members out over here come in, because they come in during that creating phase of designing and building. We've got a couple of operators in here too that have attended this webinar. These are the ones that operate the tunnel once the tunnel is delivered and handed over. And then obviously we have an end-of-life renewal or disposal team that looks after it. So the standard is written basically to cover all of these life cycle phases of an asset. Now to really delve into the Fire Life Safety suite of standards. The way our standard suite is set up, we have the designation TS0008, which is the Fire Life Safety Suite. So you would see part 1, which is the overall principle standard. That's a multimodal standard that sets out the engineering and the assurance expectations. Then we delve into mode-specific standards. So an example of that is part 2, which is our station standard, deals with obviously our train stations, our tunnels, which is what we're going to be expanding and talking about further. The ancillary facilities, which is where we have our stabling and maintenance yards, our services facilities, also our substations. So all of this, we have unique over and above Australian standard and National Construction Code transport requirements that we require for assurance. Then obviously all of these wonderful fire systems that go in, we have to maintain them. So we've got a maintenance standard that sits in complementary with AS 1851. The 2 other standards you're looking at is what we're working on currently. So my team's working on that. One of them is the bushfire management standard that we're working through till the end of the year. And then further, we have plans to start working on a guideline for evacuation of mobility impaired people in the rail environment. So the earlier shout out that I gave to the folks that I work with at Rail Fire Brigade, Sydney Trains and Metro, they are big contributors to a lot of these standards. So again, what is part 3, the tunnel standard? It covers the rail tunnels, the road tunnels, pedestrian and bicycle tunnels. So we've got a few of those that connect to our train stations and go under road surfaces. Services tunnels, some people might ask, what is a services tunnel? The services tunnel is basically where we have substations that's above ground, and we've got the rail tunnels below. It's the connection from the substation to the rail tunnel where we're taking all our high voltage cables and everything else through to feed the rail tunnel below for the trains. The standard also talks a big part about the fire brigade firefighting requirements and principles. So these standards are developed in conjunction with Fire and Rescue New South Wales, which is our state's fire brigade. And we build a lot of their requirements into this. So we set that baseline expectation of this is the minimum equipment that we expect to see to help fire brigade do a firefighting intervention should the worst happen. Naturally, no standard can live on its own. This tunnel standard is part of the civil standard suite. So we interact heavily with TS 01722, which is the overall civils tunnel standard. And sitting parallel to me, there's a team that's called the Service Systems and Equipment team. They are working on the smoke management aspect of the tunnels and also the electrical and hydraulic requirements of the tunnels. So delving just a really high-level overview of what we expect to see as a minimum with our rail tunnels. I did see someone in the chat talk about train cars and whether we take the whole thing into account. We actually have minimum scenarios that need to be modeled when you're designing the rail tunnel. So when we've actually got a standard TS 03996 that talks about train fire size to use in terms of what megawatts. The new fleet and a lot of our recently procured fleet is designed in accordance with EN 45545. So that gives you a baseline understanding of what we're looking at. Then we also require someone, if they're working on our rail tunnels, to model fires as they're doing their fire engineering, model a track vehicle that may have caught on fire. Carol talked about that earlier, if I believe that was a track vehicle or a maintenance train. Infrastructure fires, so if one of our cables or something else was to catch fire, is the tunnel designed and ready to cope for it? And of course, cross-passage, cross-passage spacings and fires and stuff like that. So FRL, obviously for those in Australia know fire resistance level. As a base minimum for a lot of our equipment rooms, we ask for a 2-hour fire rating. And as we go above that around the tunnel, we ask for 4 hours as a minimum. This is not to say that all the tunnels are designed to that. Some tunnels are designed more than that. This is just the standard setting the base level minimum expectations. Again, with our detection system, for those in Australia, we follow AS 1670.1. That's the detection standard. This talks about where we would need detection as a minimum in what rooms and why we need it. Suppression systems, you're going to ask me why suppression inside a rail tunnel. It's not the actual rail tunnel, but the ancillary rooms that service it. Whether you want to put a sprinkler system or another type of alternate suppression system, we're open to that. But the standard does talk about needing something like that. A big part of what we're doing is a lot of firefighters on the call, Gerard and Braden, who's my colleagues from IFE, are firefighters, so they would know the standard inside out, which is AS 2419. That's the fire hydrant system standard, and where we expect to see booster assemblies. So when the fire brigade does show up to a fire, where they park their trucks, how they can connect into the tunnel hydrant booster systems and boost all the hydrants in there. Smoke management, Dr. Ricky talked about it. I mentioned my colleague is actually working on that other standard for 04955.5. Currently, a lot of our major new metro tunnels are provided with that smoke management systems. I know a couple of the engineers are online, so it's good to see you guys over here. Extinguishers, obviously in Australia, it's AS 2444, which is the fire extinguisher standard. We have cross passages for evacuation, where we expect to see those fire extinguishers within the cross passage. And then egress provisions. Fire engineering does play a big part in that. We want to model it. We've set the absolute maximum, but we want to work through that criteria in terms of cross passage spacing, track access ladders, raised walkways, and the like, that will help someone evacuate in the event of an emergency and also facilitate firefighting intervention. Now, coming to road tunnels are a little more detailed because, as you can imagine, we see much more incidents in the road tunnel. It's a higher frequency of accidents, higher frequency of things happening and going wrong. So the minimum scenarios we ask for is light vehicle fire, heavy vehicle fire, infrastructure fire, and then reduced visibility from bushfires where tunnels are running through bushfire-prone lands. How will that affect visibility inside the tunnel? And then as a minimum, we stress that it's 50 and 120 megawatt fire scenarios. And then we are also looking at, we have a separate standard and risk assessment criteria for transportation of dangerous goods in tunnels. As of right now, we don't have DGVs in tunnels, but this standard helps look at the risk assessment and assess whether the tunnel can facilitate DGVs in that tunnel. A big part of that assessment is working closely with our fire brigades to understand if it is possible or if it is not. Again, fire ratings, it's pretty much the same. Those are the bare minimum that we ask for in terms of services rooms, and then the structure of the tunnel. Detection determined through what we call in Australia the fire engineering process, in equipment rooms as a bare minimum. In Australia, at least in New South Wales, we've got the fire suppression. Whether you want to use a deluge system or a water mist system, that's up to the discretion of the designer, but there is that option to look at either one of them. And then the foam suppression is where we look into our tunnel drainage system to make sure that we're not reigniting any combustible fluids in there. Hydrants, again, provided in accordance with AS 2419, which is the Australian fire hydrant design standard. And it's dual water supply, so we have backup for all our firefighting systems. Smoke management, a big part of it is the fire engineering process. Like Dr. Ricky mentioned, a tunnel just depends on the geography you're designing the tunnel to, which means you need to actually model it based on what is in front of you. So we leave that up to the project team to work through that smoke modeling requirements. The extinguishers, first attack options, in staff rooms, our tunnel control rooms, electric switch rooms, and plant rooms as a bare minimum. In New South Wales, we've got emergency cabinets. We call them FIPs, Fire Emergency Equipment Points. And we also have flame traps, which is what I was talking about earlier, where the tunnel drainage system. So every 50 meters, we require these in there. We've got the access and egress positions requirements. So the fire engineering process works through that. And there's another slide that will give you the bare minimum space, the maximum spacings we will look at. This is the summary of all of that. So it's just a summary of what I've just spoken about. What I'd really like to highlight in this is a lot of it is based on fire engineering because of the unique requirements of the tunnel that is driven by the geography of where that tunnel is. Whether it's a straight tunnel, curved tunnel, different inclines, different grades, we really need to look at that and then model it from there. But as a bare maximum, we will say we want our egress passages, cross passages for rail at 240, at 120 meters for roads, 60 meters for pedestrian and bike tunnels. And services tunnel, we ask for an unobstructed width of 850 millimeters. The reason for all those numbers, especially the 240 and 120, is because we work closely with our fire brigade to understand the capacity and the workload that a firefighter can sustain that Carol talked about. A big part of it is the air consumption, how easy it is for them to move back and forth, what's the workload and stress on them. And then from there, we work through that. Not to say that we want to look at other ways, but that is based on engineering analysis and talking to our fire brigade and understanding different mechanisms that pull that. And that's pretty much it, Gerard, for questions. Open for it, and I'll leave it up to you to run everything.
Awesome, thank you. That was really good, Jace. It was really good to see the owner or the operator's perspective on tunnel fire safety. I'll just bring up the slide window for questions and we'll start with some questions. Now, I've had some questions through the chat. I'll mute myself during and I'll just go question about. So the first question is for Ricky. Ricky from Tax, and I'm going to absolutely butcher some of the pronunciations of these names. Ricky, did you consider the peak heat release rate for a railway carriage fire, specifically within a tunnel environment, or just a railway carriage fire generally? I ask because the peak heat release rate can vary significantly depending on carriage interior materials, suppression systems, and the interaction with the tunnel ventilation.
Yeah. So, I mean, the data that I showed in the graphs where the data is, I mean, heat release rate data is process data, but it was as close as you can get to raw data from the actual experiments. Now, of course, when we do fire tests in tunnels, nobody gives you their brand new current spec railway carriage to set on fire. So at the time of those tests, every single one of those vehicles was an old vehicle. So absolutely, um, the absolute numbers on the screen will vary depending on the carriage design, depending on how many doors and windows are open, or anything like that. Um, but the overall trend, and as I say, this shouldn't be a surprise to anyone, but if you ventilate a fire, it has the capacity to grow much larger. Um, and so the peak heat release rate of a fire which you're blowing ventilation at will be larger than the peak heat release rate of a fire where you are restricting or minimizing airflow towards. Um, Now, the actual numbers will vary, and yeah, what we are seeing is um, there is certainly less flammable material in the inside of railway carriages than there used to be, but there's not zero. And so the trends will remain the same even if the numbers are different. So I do like to point out that it's the sort of trends in behavior rather than the numbers. Don't get hung up in the numbers. The heat release rates will be different, um, but what you do with your ventilation system still affects the fire. I think that answers the question. I hope.
I got it. So thanks, Ricky. That was great. Next question's for Carol from Yenny Gomez. Carol, in steeply sloped tunnels where buoyancy effects make maintaining critical velocity increasingly difficult, and where high ventilation velocities may contribute to larger, faster growing fires, should the design intent shift away from strictly eliminating upstream smoke and instead prioritize controlled smoke management to maintain tenable conditions for assisted evacuation, particularly for occupants unable to self-rescue? Reading that, I think that's actually meant for Ricky.
Yeah, I
Sorry,
think
Gav.
that's for me as well.
Yep.
One thing it's not possible to do is I can't talk about a general tunnel, an average tunnel, a typical tunnel, because there simply isn't one. And if you've got a steeply sloped tunnel with local peculiarities, I can't generalize. Um, this is where I mean, this is the job of the fire safety engineer comes in. I'm an educator. I like to remind people that fire doesn't behave itself, and if you change the ventilation, you change the fire. It's actually the job of the engineers to come in and look at the precise, the specific incident or the specific case that they're doing and work out what is the best thing to do. Consider the scenarios. What would happen if we used the ventilation in this way versus what would happen if we used the ventilation in that way. Um, I mean, design for self-rescue, if it's possible, is always what we should try and do because with the best will in the world, with the best firefighters in the world, they're not going to get there in the first few minutes of an incident. And we've often seen again and again when things do go wrong, the first few minutes of an incident are crucial. Um, the thing you can achieve in the first few minutes of an incident is setting the ventilation to a certain set of settings. Um, And hopefully, if your engineers have done their job right, they've thought through the actual consequences of what might happen in those, and uh, how those ventilation settings will assist egress and self-rescue. But there is no one size fits all, and that's for sure.
Thank you, Ricky. I think you touched on a really good point there where we have to understand the variables and the outcomes, and then we can do the calculations for the specifics. So I've got one for Carol now, and I'm pretty sure it's Carol because it's got SCBA in the question. So, Carol, regarding the 275-meter distance for a single BA bottle, is that calculated as one-way travel to the fire only, or does it include both the approach and return distance? And this one's from Minna Abdo.
Yeah, so this is actually a 275-meter deep tunnel. So actually, they're going to walk 550 meters.
Awesome.
Does that make it clear?
It does for me. Minna, if you're in the chat, are you happy with that? I'll give you a couple of seconds. Well, I've got you here, Carol. I've got another one from Tax. What was the rated capacity of the single-cylinder BA set used in the assessment? How was the 50 bar safety margin and remaining duration determined for tunnel firefighting conditions?
So the standard bottle we use is a 6.8 liter bottle that's pressurized at 300 bars. So which gives us like 2,000 liters of air. The 50 bar margin is standard, I think, all across the fire service. It's 1/6 of the contents of the bottle. So we have 250 bars usable air. If you divide it by 2, you have 125 to go in. And so at 175, the 50 reserve and the 125, that's when a beep goes to indicate you're at half of the usable air. And if you go back, then you should be safe in theory.
Thank you, Carol. That was great. I'll move on to Jason now. Jason from Minna Abdo. Is the FRL based on AS 1530.4 testing, or is it assessed against the RABT tunnel fire curve?
So our station standard looks at the RABT fire curve, and that's what we assess all our requirements on.
Awesome. Is he frozen, or is everyone frozen? Can everyone hear me? Carol,
Yeah,
can you
we
hear
can
me?
hear you.
Yes.
Yeah. Sweet. It's just you're frozen on screen, Jace. Was that the end of it? Oh, there you are. All right. There you are. You connected again. Too easy. All right. This one's back to Ricky. Ricky from Conrad Stacey. Did your work examine transient and fire growth and optimal velocity concepts rather than relying primarily on steady state critical velocity assumptions?
So the question is, does my work rely on? If we go back 25 years to when I did my PhD, I was looking at the growth rates of fires. So certainly there, I was not focused on steady state. And certainly the graphs I showed in my presentation were the whole evolution of the fire, not steady state. So I think to be honest, I think, and I hopefully those in the room that have been my students at one point will remember, there is no such thing as a steady state fire. We never have that. A fire changes, it adapts. If the ventilation changes, the fire changes. If something else changes, the fire changes. A steady state fire is a myth. And so I don't think we should design for steady state fires. And I don't think, well, they don't exist, so I don't know. I've now forgotten half of what the question was.
So I'll just jump in there, Gerard, just to talk about what Ricky said. Being an owner and operator, or working for the owner and operator, I get to see through the CCTV the fire. I have never seen a fire behave the same way. I've never seen two fires act the same way. So while I understand we do model and we work through it, fire will do what fire has to do.
So I've got one from Matthias here too. And I think it's to you again, Ricky. So the fire is shown to have a higher heat release rate in experiments with forced longitudinal ventilation. How do temperatures or heat fluxes, sorry, it just moved on the screen. How do temperatures or heat fluxes compare for the first responders approach? If a 50 megawatt fire is easier to approach from the upstream, it is worth to consider in the decision whether or not to care about the critical ventilation compared to other factors that a lower heat release rate fire may induce. And I might get Carol to jump in here too on this after you've had a crack, Ricky.
Yeah. Okay, so I mean that's a very important question, and I mean there isn't an easy answer. I actually don't know if people have studied this directly. Um, Certainly, I mean I can model in a CFD model, the fire with air blowing it and a different fire with air not blowing at it, and it will give me a prediction of heat fluxes, but I know from experience that the model will give me the wrong answer for heat fluxes. So the what the fire brigade actually experience as they approach a fire is not something state of the. I mean, apologies to anyone that thinks CFD models are magic and can do everything. They can't. I don't think that question of heat flux can be answered theoretically. It has to be answered operationally at the moment because you guys know what you actually experience. My gut feeling, particularly as the fire brigade can approach a fire in kit, which enables them to breathe in a smoky atmosphere. It gives them some protection from the heat. I think that it's probably better to approach a fire where the smoke is not completely controlled and the ventilation is not causing a raging inferno. So I think you want to err on the lower ventilation side, but this is just my opinion. I'm not an operational firefighter. Maybe your experience tells you something else, and I don't know. But I think if you're going to completely control the smoke from a truck fire, you're going to have a very large truck fire that the heat fluxes will be such you can't get close to it anyway. But I don't know. Maybe Carol has more insight here than I do.
Well, the
Carol?
question is what is burning? So in our tunnels, we don't allow for trucks because of the high heat release rates, and so we only have cars and vans, which means the heat release rate is per definition limited if it's only one truck or one van or one car burning. And then from my experience, it's easier uh, to put on the ventilation so we can approach at least from one side in good visibility. And then you have a fast response and a quick knockdown, and then the problem sorts itself out. Whereas if you don't have ventilation from both sides, it will take a lots of time to get there. Now, on the other hand, to bring some nuance, if it's a truck where you have like 50 megawatts, then it will only be approachable from one side because the ventilation will push all the heat, will increase the heat release rate. So attacking it from the wrong side will not be possible for the fire service. But the trade-off is on the other side, you will be able to find the fire and to approach it quite quickly, and then you can throw large quantities of water at it. Depends on the traffic situation in the tunnel. But if we can drive up with a fire truck to close to the fire, connect to the water system in the tunnel, we can throw 2,000 liters a minute to that fire, and then it will decrease in intensity quite quickly.
Thank you, Carol. All right, I'm going to flick to Jason now. Jason, for tunnel fires, how do we appropriately account for human behavior and evacuation within the fire engineering analysis, particularly considering rapid smoke spread, reduced visibility, occupant decision-making delays, and the typically extended travel distances to places of safety?
So this is also down to the fire engineering and the modeling that the fire engineer uses. The other aspect is, while it depends where you are, we in New South Wales have a lot of traffic management systems. So I don't know if people in New South Wales are here or what's the percentage. We will take over the emergency radio broadcast and start broadcasting to cars. We'll start to manage that flow of traffic into the tunnel, so we reduce the number of people in the tunnel. We'll also start, we've got dynamic signaling where we will open and close lanes and move people around. So we reduce the number of people in there. We've also, besides that, there's the smoke management systems that kick in and start to pull air. We in New South Wales work closely with fire and rescue teams. We have a tunnel that we actually test these systems in every now and then. And if you ever get to watch those, I don't know if any of those videos have made it onto YouTube, but if you put it in, you will see how quickly we clear the smoke. So that's one of the big advantages we have in here. But we do require the modeling to be modeled like that as being failed.
Thank you. So I've got one probably for everybody from Peter Hillhorst. Has any brigade developed a capability document? So has any fire brigade that any of you three panelists know developed a capability document?
Okay, so I know Fire and Rescue New South Wales have a SOG, which is your officer guideline. I'm not sure about capability document. We do have what their equipment is capable of that they publicly publicize on their website in terms of their trucks and everything else. I'm not sure if we're talking capability of the individual firefighter's capability. That would be very hard, because earlier in the year I also attended a presentation by Carol where he went through, I love his story about the person who was an athlete that ran marathons and used the most oxygen out of everyone.
Yeah, I think it's more around, has a capability document been done by the brigade, such as FBIM, but specifically for tunnels?
Well, I think there has been some work done, but there's lots of uncertainty. There is stuff missing. For example, the base of my research is we don't know how much air a firefighter uses and how far he can go in a tunnel. So I've done some pieces, but it's just small pieces of a complete puzzle. So IFA in Switzerland, they have done lots of work in thinking about how we can fight fires in tunnels. But there's still a lot to be done. My knowledge, nobody has a complete capability document. Lots of fire departments have done good work to solve part of the problem, but I don't think somebody has a complete document as intended in the question.
Ricky?
I'm not sure I have an answer to that. As I say, I'm an educator working in a university. I can't really comment on whether such a document exists.
Thanks, mate. All right, back to Jason. Jason, what do you mean by a dual water supply for road tunnels?
Okay, so dual water supply, specifically in our road tunnels, because of the large use of water, is two 2118 and 2419. It's two independent sources of supply. Especially for our sprinkler system, we have dual tanks because we know the town main will never be able to cope with that. Sometimes for the fire hydrant system, we may be able to depend on the town main, but a lot of the times tunnels in rural areas where we don't have a big town main, we ensure we have two independent sources of water supply, being either two tanks or one tank in town.
Thanks, mate. Thomas Connolly to Carol. Carol, in tunnel firefighting operations, do you advocate for attacking fires from both sides in all tunnel configurations, or is an upwind upstream approach still considered the preferred operational strategy depending on tunnel type and ventilation conditions?
So our procedure is based on attacking from both sides, and there is tactical reasons behind that. In theory, you think about a fire and it's somewhere, but in practice, there is two ways to enter into that tunnel. Could be a portal, could be an emergency exit. And in practice, often you don't know where the fire is compared to those exits. You could even be mistaken, and all your two exits could be downstream or upstream. So the idea is to entangle the fire, to go from both sides, to be sure at least one team gets close to the fire quickly and puts it out. It's because of the uncertainty. Also, when encircling it, on both sides, we can encounter victims and try to save them. And if you only attack from one side, preferably the side where there is less smoke, you will be able to knock the fire down. But it's only after the fire has been knocked down that we can pass the side of the fire and go look for victims on the other side of the fire. Whereas if you come from both sides, it gives people who are still stuck in that tunnel most chance of survival.
Thanks, Carol. While I've got you, there's another question here from Johnny Hamill. Given that your study focused on search and rescue operations using mobility canes, do you consider it realistic that, during a real tunnel fire incident, initial attending crews would have sufficient capacity to effectively utilize mobility canes while simultaneously managing hose lines and conducting and undertaking active firefighting operations?
Well, yeah. So the idea of the mobility cane is it's a way to advance more quickly in a zero visibility environment in tunnels. So the first crew, the recce crew, they don't have to do anything but watch and advance. For them, it's a real game changer. Then the fire attack crew, they have to advance. And in our system, that's a station officer with 4 firefighters. So then the station officer can guide them whilst the others are deploying the hoses. Same thing for the search and rescue crew. They will follow and they can use the mobility canes to search a tunnel. For example, if there is a bus in the tunnel and somebody is underneath, a good way to swap the area underneath the tunnel is just to swap with the mobility cane underneath it. It's also between cars. It's once used to it, once trained how to use it, it's a very good tool. Of course, as soon as they become stationary, because they start fighting the fire, they have the counter reaction force of the water flow, then they will no longer use the mobility cane. But it's to advance large distances and to search, the mobility cane is really an advantage.
Right. That was really good. All right, to Jason now. Given your, if this one's again from Johnny Hamill, given your study for, I think we've done that one, Braden. But yeah, we have. All right, I think we've caught up with all the questions.
Okay.
Which is really good. Thank you so much to everyone for attending tonight. We've had a maximum of 190 people in the webinar, which has been amazing turnout from everyone. This webinar will be available, Jason, online?
Yes, so just for everyone's information, it will take us a couple of weeks to just edit this and put this back together. And we will be posting it on our IFE YouTube page. For members of IFE and others that do get the IFE newsletter, we will also be sending a link within that newsletter, and check back in 4 weeks probably on our LinkedIn too, and we'll put a link to the video of this webinar on it.
Awesome. So for everyone that's still online, if you are in Australia or if you think the Australian branch of the IFE is worth joining, there's a link to the membership options. And for joining our membership, I'd like to remind you that AFAC conference is coming up. We do have the IFE streams. We're lucky enough to have Jason and Ricky speaking. Carol has been out and will probably be out again very soon. or in the not too distant future. On behalf of IFE Australia, I want to thank each of you, Jason, Carol, and Ricky, for giving your time tonight to help us understand more about the tunnel fire problem. And I think this is an important piece of work. And if the participant numbers are anything to go by, I think we could probably do a series on these, Jason. So I'm hitting up the president right now in front of you all to get more content out there for you.
Nothing like
anything,
isn't it, Gerard?
Exactly. Anything you'd like to add, Jace?
No, thank you everyone for coming by. And yeah, like Gerard mentioned, IFE Australia exists because of our members. All our feedback is really, really taken seriously. And a big shout out, obviously, to Dr. Ricky, who's going to be coming out to the IFE stream in AFAC in August. And Carol, who had actually come before to Australia, I think it was February, right, Carol? When we did the International Fire Instructors Workshop. So hopefully we can plan something in the future and do a combination of both firefighting and engineering side by side.
That's the dream, isn't it? I'd love to do an event where we do both side by side. All right. So unless there's any closing comments from the panelists, Jason, anything you want to say?
No, I'll leave it up to Carol and Dr. Ricky if they would like to say anything.
Carol?
Well, happy to have been here. 50 minutes is really short, but great event and great number of people showing up. So thank you.
No dramas. Dr. Ricky?
Yeah, just thanks for the invitation to do this and also to come out to Melbourne in August. Although you just said you had Carol out in February, so you had him out in the summer and you've invited me in the winter. I don't know. We'll maybe do something.
We'll take the constructive criticism on board, Dr. Ricky.
Yeah, but
we didn't want to shock you. I couldn't stand around with an umbrella keeping the sun off you. I'm sorry. Alrighty. So thank you to everyone that joined. We'll call it there tonight. And yeah, it will be up for everyone to see. So thank you very much. And before we go, thank you to the board of the Australian National Branch of the IFE for doing all the hard yards behind the scenes, especially Marianne Foley, who worked really hard to put this all together. So again, shout out to Marianne. All right, guys, thank you very much. Have a great night.